Hello there. You're watching Differential Questions by Alex. That's me. All right, so today's topic is about second order linear differential equations. And specifically, we're going to talk about the existence uniqueness. So I want to give you an outline for the next few topics that we'll cover. So the main idea is that we are going to talk about second order linear differential equations. And under this category, we have all these topics that we're going to talk about, not today, but this is like the terminology definition section. But today in this video, we are only going to talk about the first topic that I have in the first bullet. So that's called existence uniqueness, and then in a separate video, I'll talk about the other topics. All right, so now let's start with the type of equations that we want to deal with. Okay, so these are second order because the highest derivative that we see is going to be the second derivative. And it's going to be linear because as you see, the y prime, the y, and the y double prime don't have any powers, or they are not inside of another function. All right, so this is a linear second order differential equation. So this is your equation, and then you also have the initial conditions. Okay, and I want to give you a specific example to show you how things might look like. Okay, so here on the example on the bottom, the a function is x squared minus 4. The b function in the example is x, just the function x, and then the c function is the cosine of x. So just to give you an example, and then also the g function is given by this in the specific example that I'm giving you here in the bottom. All right, and so now also we have the initial conditions, and for this section I would not say too much about the initial conditions except for today. And so just to give you some specific examples how the general setup might look like in a very specific case. All right, so these are the type of equations that we want to deal with, okay? So today is about terminology, but before we actually try to solve this second order linear differential equation, we want to know, should we even start solving for the solution? So again, you have a differential equation with the initial conditions, and you want to know what is the formula for the y function. So what is the formula for the y function that satisfies the differential equation and also the initial conditions? So if the problem does not have an answer, does not have a solution, then you should not go ahead and try to find something that doesn't exist. So that's why we care about the existence uniqueness theorem. And so we need to talk about this just slightly, briefly, and then we'll see how this is actually going to help us to know something about the problem before we actually even start solving the problem. Okay, so what this theorem is telling us is that whatever the differential equation is, as long as the a, b, c, and the g function, which are the a, b, c, g functions, as long as those functions are continuous on the specific interval, and as long as the a function that you have in the very beginning, as long as those two conditions are met, then the entire problem has a unique solution. Okay, the entire problem has a unique solution. Okay, meaning there is a function y that has a formula. We don't know what the formula is yet, but we're saying that there is a function y that satisfies the differential equation and also the initial conditions. But you have to check those two conditions on the theorem before you can say that. All right, so today I want to kind of get comfortable with this. That way we know when to attack a problem or not. All right, so the first question that I have here is, I have a specific differential equation with initial conditions, and then the basic question is, does this problem have an answer? Okay, so notice that I actually already gave you the answer here on the bottom, but for right now, just ignore this. Ignore that I already gave you the answer to this problem. I'll give you a formula already for the problem. But what I want to tell you is, well, let's go back and then check the conditions that we have. Okay, so remember that we have a y double prime plus b y prime plus c y is equal to the g function. And so we need to identify the different pieces here. Okay, so the a function is going to be 1. So that's the a function. The b function is going to be 0. There is no b. And then the c function is going to be -4. Okay, so that's the c function. And then the g function is going to be 12x. Okay, so we have to identify the a, b, c functions and also the g function. So we have the function that is always 1, the function that is always 0, the function that is always -4, and the function 12x. And then the first condition was saying that these 4 functions have to be continuous. And in this case, are they continuous? And For us, yes, they are continuous. So now we need to go into the condition number 2. Condition number 2 says something about the a function. So the a function cannot be 0 on the specific interval. And so the a function for us in this problem is, let me just write it out here again for you. So ax is equal to the function 1, the number 1 always, and then this is never equal to 0 for all x's. For all x's. So that means that we have also satisfied condition number 2. So condition number 1 is satisfied, condition number 2 is satisfied. And because of that, then we can use the existence uniqueness theorem to say that this entire problem, there is a function y with some formula that satisfies the differential equation and also the initial conditions. Right now, we don't know what the formula is, but we can say that there is a formula, a function y that satisfies this entire problem. And so now let's go into the red underlined stuff that I scratched out. Okay, so I'm going to erase all this and I'm going to show you what the solution to this problem is. Right now, I haven't told you how to get to the y formula. I'm just telling you that the theorem is telling us that there is a formula that satisfies a function y that satisfies this entire problem. And now the formula that satisfies this is the following. This is the function that satisfies the differential equation and also the initial condition. Okay, and then in this chapter we're going to figure out how to get to that answer. Okay, we're not there yet, but right now we're just trying to get comfortable with the terminology, the type of problems that we're dealing with, and then this idea about the existence uniqueness. So we check those two properties and then we can say that there is a solution, and right now I'm telling you what the solution is without showing you how to get that. We'll get there soon. All right, so let me give you another example. Okay, so and again, let me scratch this out. This is actually the solution, well, the partial solution to the problem, but let's ignore that. And then the question is asking us, for this specific differential equation with the initial condition, is there a function y that satisfies this problem? And then secondly, is there only one function that satisfies this entire problem? Okay, so there are actually two questions here. One is there a function y that satisfies this problem? Is there a function y that satisfies this problem? And then separately, is there maybe two functions y that satisfy this problem? Or maybe 3, or maybe 4, maybe more. Right, so now let's go back into our check. Okay, so let me write down this as ay double prime plus by plus cy is equal to the g function. So let me write it out this way. Okay, so the a function is what's x squared, the b function is negative 2x, the c function is 2, and then the g function is just 6. And now the first check that we need to do is we want to know if these functions are continuous. We want to know whether these functions are continuous. That's the question. And in this case, they are, because all of them are polynomials or just constants, which are technically are polynomials. So that's the first check. Okay. So we check that the a, b, c, and g functions are continuous. Then we have to look at the a function, and this is again the x squared. And then we don't want this to be 0 for x in the interval. Okay, so now go back to the initial condition. The initial condition here is 0. What do you know about if you plug in 0 into the a formula here? Plug in 0 into the a function, then you get 0. Okay, so this is a red mark, meaning that this is not going to be true for our problem. So we did say that we do have a green go on the item number 1, but for item number 2, we're getting this troublemaking situation. We have that if we plug in a number, specifically 0, we do get 0, which is something that we don't want. Okay, we don't want 0, but in this case we do. So what that means is that we cannot. So the question is asking, can we use the existence uniqueness theorem? And in this case, we cannot use the theorem. So the answer would be no. But just because we say no to the about being able to apply or use the existence uniqueness theorem, it does not mean that there is no solution. Maybe there is no solution, or maybe there is one solution, or maybe there's infinitely many solutions. Okay. So what these two steps are just telling us is that we cannot use the theorem. So I'm going to give you what the answers in plural are. Okay. So the answers, so this is our solutions with an S. We have all these functions that satisfy the differential equation and also the initial condition. If you were to plug in the y function into the differential equation, the output will be equal to 6. If you were to plug in 0 into your function, it will give you 3. If you plug in 0 into the derivative of this y function, it will give you 1. Right, so what this means is the following. Suppose that I plug in c equal to 1, so I have x squared plus x plus 3. That's where c is equal to 1. And actually, I need to be a little bit careful here because of my notation from before. So let me write this as a k. So this is the letter k, because I don't want to get you confused with the ABC that we talked about before. This k, let's just make it a different letter. That way we don't confuse it with the ABC from before. So now whenever the k is equal to 2, you would write down the y is equal to 2x squared plus x plus 3. And when k is equal to, you can just choose another random number. You can put a pi if you want to. So y is equal to pi x squared plus x plus 3. And you can plug in any other number that you want to. So you can plug in a whole bunch of numbers, infinitely many numbers. And what we're saying is the following. We're saying is that all these functions, no matter what k number you plug in, all these functions plug in for y into your differential equation and also into your initial conditions. All of those functions satisfy the differential equation and also the initial conditions. So we're saying that infinitely many functions satisfy this differential equation and initial conditions. So we have infinitely many solutions to the problem. So do you see that just because we cannot use the theorem, it does not mean that there is no solution. In this case, we have actually infinitely many solutions. All right, so that's just a little preview of what can happen. So now I want to give you a different flavor of the type of questions that you might see for this type of topic, about the existence uniqueness. So the question says, find the largest interval centered about x equal to 0 for which the initial value problem, which is given here, this is the differential equation, and then these are the initial conditions, has a unique solution. The question is not asking you to solve the problem. We're not there yet. So actually, this problem takes a little bit more to solve this problem. So this question is asking us, for what type of interval can we say that there will be only one solution to the problem? And then here, the center of the problem is this x equal to 0. All right, so now let's go back to the drawing board. So we have the ay double prime plus by prime plus cy is equal to the g function. And what we care about is that the a, b, and c are continuous, and then you can kind of check that they are. But let me just write down the a function here. So the a function is the one that is more important. The b, the c, and the g in this case are, well, let me just highlight them. I'm not going to label them, but the 3 and the x, they are continuous. So that's good. But now let's focus on the a function. So we don't want the a function to be 0. Notice that when you plug in 2 into the a function, this will give you 0. So 2 is a troublemaker. This says troublemaker. Let me just call it a troublemaker. And so what that means is the following. Okay, so let's draw the xy plane, and we're going to label our troublemakers there. So 2, and I'm going to put a hole there at 2. All right, and now where is the center centered at x equal to 0? So here's the points x equal to 0. This is the number 0 in red, not a hole. So this is the point 0. And so now we want to put a interval around 0. So we want to put an interval around 0, but we want the interval to be as big as possible, but as big as possible that does not contain the troublemaker. Okay, so if I make the interval just slightly bigger, I will be even okay. Okay, and then the question is asking us for the largest one. And so here, the interval that I need to choose will be the following. So it will be from -2 to 2, but it's going to be from -2 to 2 with open parentheses. So this is the interval that we care about. All right, and so what this means is the following. If we have this differential equation given to us, and if we have these initial conditions given to us, and then we're saying that we want the interval to be centered around x equal to 0, then the interval that we have to focus on will have to be the interval -2 to 2. And then if we do have this interval with the differential equation and with the initial conditions, then the theorem is telling us there is going to be only one solution to the problem. Okay, so basically what we're saying is that we are going to choose the interval so that we can actually get a solution, not only a solution, but we can only get one solution. All right, so that's a different type of problem. Just think about it, and you'll see that it's a little game here to figure out the interval. All right, so now what I want to do is I want to give you some terminology for the chapter. Okay, and so again, I wrote down the differential equation that we're dealing with here, which is this second order linear differential equation, and we want the a, b, c, and g functions to be continuous. And we do care about the interval. This just means that the x belongs to the specific interval. And we care about the interval because that tells us whether we do have a solution to the problem or not a solution to the problem. Not only that, we also have to be careful with the a function. The a function cannot be 0 on the specific interval that's given to us. All right, so whenever you have a g function here, this equation, this differential equation, which I call it an ODE, this is called a non-homogeneous equation. Non-homogeneous equation because this is not 0. The g function is not 0. So that's what the non-homogeneous means, not 0. So now I do need to make a clarification here. So previously, in the previous, I guess 1 or 2 chapters ago, we talked about something about homogeneous functions. Okay, so we are in a different chapter now, so don't confuse the non-homogeneous ODE with homogeneous function or non-homogeneous function. What this means is that if you had a function, let's say you had the function xy is equal to x squared plus y squared. So this is a little bit of calculus 3 here now. So you have a function, and then this function is called a homogeneous function if whenever you substitute the x with a tx, and if you substitute the y with a ty, you can do a little bit of algebra, and then you can kind of factor out, in this case, you will factor out t squared fxy. Okay. So this is what it means for the f function to be homogeneous. It means that if you substitute the x and the y with the tx and ty, then you can kind of factor out the t and essentially get the function f back again. And the 2 here, that's only specific for this function because this is degree 2. But if this were degree 3, then the t will be to the power 3. Okay, but that's roughly what the homogeneous functions are. So that's one topic that we covered before, and then this is a little bit of a Cal 3/algebra. And then previously we also talked about the homogeneous differential form. Okay, homogeneous differential form, which are in the differential equation class. And then those were of the following form. We were saying that we had mxy dx plus nxy. So we have 2 functions, the m function and the n function. And so we have this differential equation. And then what we were saying is that a differential form or the equation is called a homogeneous differential form if both the m and the n are homogeneous functions. Okay? So that was the previous, in the previous section. All right, so just a little bit of review here on the very bottom. Okay. But now we're dealing with the second order differential equations. On the bottom, we were dealing with a first order differential equations. Now we are dealing with second order differential equations. And in particular, this is, if you have a g, this is called a non-homogeneous equation. So if you don't have a g, suppose that you have a 0 instead, suppose that you have a 0, then it is called a homogeneous equation. A second order homogeneous equation. And again, the a, the b, and the c, they are assumed to be continuous for us to actually do some work here. They, in practice, they don't have to be continuous, but that's where the advanced mathematics comes into play. But for our purposes, the a, b, and c, as long as they're continuous, we're good to go. All right, so that's it for what I want to say about this topic. And remember, we are now dealing with second order linear differential equations, and we just talked about the existence and then uniqueness. And so this is just the first topic, and just to give you some terminology. And so on the next video, I'm going to talk about a homogeneous equation, but I'm actually going to talk only about the principal superposition. Okay, so it's a very lengthy section. This entire thing is just a section about second order linear differential equations. And then we have all these different topics. So I'm trying to break it down. That way it doesn't get overwhelming in just one single video. All right, so that's all I'll say for this. And I'll see you in the next video about the principle of superposition.